The James Webb Telescope gave us a stunning first look at the depths of our universe.
This is the first time we get to orbit Mercury.
When we imagine life on other planets, we have to imagine that the environment on those planets will determine.
James Webb has just revealed the shocking information that NASA concealed about Mercury, and it is rather damaging. For a long time, scientists believed that the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It should already be a dead planet. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?
Now, thanks to powerful telescopes like James Webb, scientists have stumbled upon these secrets. But what they found is so weird. There is something moving that they never saw anywhere else. Such a stunning revelation could even lead to crucial missions to reveal a terrifying truth about our universe. Join us as we shed light on the dark shadow that Mercury has kept under wraps. Mercury, named after the Roman messenger god known for his swiftness, is the closest planet to the Sun. This planet certainly lives up to its name in terms of speed. It is the fastest planet in the solar system, racing through space at an average speed of 29 miles per second. Despite its rapid pace, Mercury takes just 88 Earth days to complete a full orbit around the Sun. This makes its year significantly shorter than Earth's. In fact, it completes nearly 4 orbits in the time it takes Earth to complete one. In addition to being the fastest planet, Mercury is also the smallest. Its equatorial diameter measures only 3,032 miles, which is only slightly larger than Earth's moon. This makes Mercury the smallest planet in the solar system, smaller even than some of the largest moons in the outer solar system. Its small size and proximity to the Sun make it one of the most challenging planets to observe. It is one of the 5 planets visible to the naked eye, but its location close to the Sun means that it can only be seen during the brief periods of dawn and dusk. Mercury rarely rises far above the horizon, making it elusive and hard to spot. Although it is difficult to observe with the naked eye, Mercury's orbital position provides an interesting phenomenon that astronomers have been tracking for centuries. About 13 times every century, Mercury passes directly between Earth and the Sun in an event called a transit. During a transit, the planet appears as a tiny black dot moving across the Sun's bright disk, providing a rare opportunity to study both Mercury and the Sun in a single event. These transits, while infrequent, are a fascinating occurrence for astronomers, offering insight into the mechanics of the solar system. Mercury's motion in the sky can be even more puzzling when one observes its retrograde motion. Retrograde motion is a phenomenon where a planet appears to temporarily reverse its usual eastward motion across the sky, instead moving westward. This optical illusion occurs when a faster-moving planet overtakes a slower-moving one in their respective orbits. For Mercury, this retrograde motion happens about 3 to 4 times each year when it passes Earth in its faster orbit. On Mercury itself, the experience of retrograde motion would be even more dramatic. Due to the planet's rapid orbit around the Sun and its slow rotation, the Sun's movement in the sky would be unusual. At certain points in its orbit, a person standing on Mercury would see the Sun rise, set, and then rise again within a single day as Mercury's orbital speed exceeds its rotational speed. This rare phenomenon is a direct result of the planet's unusual orbital mechanics. Like all the planets in our solar system, Mercury formed around 4.5 billion years ago from the same cloud of gas and dust that gave birth to the Sun. It is classified as a terrestrial planet, meaning it has a solid, rocky surface with a metallic core. However, due to its small size and proximity to the Sun, Mercury cooled rapidly in its early years. This rapid cooling caused the planet to contract, preventing the escape of molten material from deep within, which in turn halted volcanic activity and other geological processes relatively early in its history. Despite its small size, Mercury is surprisingly dense. Its mass is more than 4 times that of Earth's moon, making it the second densest planet in the solar system, after Earth. This high density is largely due to Mercury's large iron core, which constitutes about 60% of the planet's volume. In contrast, Earth's core makes up only about 15% of its total volume. The unusual density and internal composition of Mercury have led to various theories about its formation. One theory suggests that early in its history, the Sun's intense heat may have stripped away part of Mercury's outer layers, or perhaps a giant impactor collided with the planet, knocking off much of its lighter crust and mantle. This theory is supported by the fact that remnants of Mercury's mantle and crust still exist today, which implies that the collision may have been a glancing blow rather than a direct hit, preserving some of the planet's original material. Mercury's enigmatic characteristics, from its extreme speed and proximity to the Sun to its peculiar retrograde motion and dense core, make it a fascinating planet to study and observe. Despite its small size and elusive visibility, it remains a key object of interest for scientists seeking to understand the formation and dynamics of our solar system. The first mission to Mercury, Mariner 10, was launched in 1973 and found that Mercury still sustains a magnetic field. The discovery came as a shock to the scientific community, who had assumed that such a small planet would have rapidly cooled and its insides would have congealed, thereby losing any means of magnetism at the global scale. The presence of a magnetosphere implies that part of Mercury's core is still churning. Mercury's magnetic field is about 100 times weaker than Earth's on their respective planetary surfaces. The sluggish dynamo means that the planet is at the tail end of its developmental stage, on its way to becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, documented that the planet's magnetic field is off kilter. The magnetic South Pole doesn't sit on the geographic South Pole. Instead, it is buried almost at the center of the planet. The magnetic field offers a glimpse of the planet's interior and a snapshot of its history, hinting at how far the whirling insides have decelerated over billions of years. Due to its proximity to our star, Mercury is hot. If we're being quantitative, it's actually extremely hot. As the closest planet to the Sun, it completes an orbit in just 88 Earth days, achieving a maximum temperature during the day of a whopping 427 degrees at its hottest equatorial locations. Mercury rotates very slowly, so its night side spends a consecutively long time in the dark, shielded from the Sun. During those times, it gets down to just minus 173 degrees. That low temperature is incredibly cold, and far colder than any known naturally occurring temperatures here on Earth. But despite being the closest planet to the Sun, Mercury is not the hottest planet in the solar system. Venus is about twice as far from the Sun, on average, as Mercury is, taking about 225 Earth days to orbit the Sun. It also rotates even slower than Mercury, spending more than 100 consecutive Earth days at a time bathed in sunlight, and then an equal amount of time in darkness. And yet, when you measure the temperature of Venus, there's a surprise. Venus is the same temperature at all times, day or night, at an average of 462 degrees, making it even hotter than Mercury. This strange occurrence did more than just puzzle astronomers when they first discovered it. It mortified them. Venus wasn't large enough to generate its own heat, and yet it was hotter at Venusian midnight than at Mercurian high noon. Why is that? Well, that is because of the main difference between the two worlds. Venus has a very substantial one that's some breezy 90 times as thick as Earth's is, but Mercury, instead of a substantial atmosphere, has such a thin atmosphere that it doesn't really qualify as an atmosphere. Instead, Scientists call this wispy layer of gas an exosphere, where the gas is so rarefied that it hardly registers a pressure reading. Mercury takes a constant beating from the sun, so its exosphere has to regenerate itself from the surface. Since the 1980s, astronomers have detected in Mercury's exosphere atomic sodium, potassium, and calcium metals with strong emission signals that can be observed all the way from Earth with telescopes. These metallic elements are not usually thought of as gases, but they find their way into Mercury's skies by dint of solar particles and meteorites striking the planet's surface. Solar winds gouge the resulting exosphere, and the interactions between the gases and sun-flung particles fashion a 15 million mile-long glowing tail behind Mercury. This tail lengthens and shrinks seasonally depending on Mercury's proximity to the sun. If you were standing on Mercury and looking up at the right time of the year, Mercury's long tail would appear into the sky as a faint orange glow, as if the heavens were illuminated by sodium streetlights. A planet perched right at the sun's maw shouldn't harbor any water, let alone ice, or so researchers thought. But in the 1990s, scientists at the Goldstone in California and the Arecibo radio telescope in Puerto Rico directed a stream of radar signals toward Mercury. The teams were astonished to observe two brightly reflective spots at the poles, likely icy deposits. In 2012, MESSENGER confirmed that the ice at Mercury's North Pole was frozen water. Laser measurements on board identified carbon-rich material on the surface that insulates an ice pack underneath. Mercury has managed to cling onto its water because it has pockets in permanent shadow. Relative to its orbit around the sun, the planet spins perfectly upright, like a soldier at attention facing a commanding officer. That means the impact craters near the poles have insides that never see any daylight. Temperatures within these davits dip below minus 173 degrees Celsius, close to the temperature where nitrogen gas liquefies. It's cold enough that ice can be stable over geological time frames. And as on most other rocky planets, the water on Mercury probably came from asteroids that crash-landed onto the surface. This water hides in Mercury's craters, untampered with since primordial times. On other terrestrial planets in the solar system, geological processes such as weather cycling have scattered the externally delivered water all around the globe. If scientists want to sample ancient ice in its pristine form in the solar system, the best source is probably Mercury's poles. Mercury defied expectations again when MESSENGER detected volatiles on the sun-scorched world. Volatiles are chemicals that can jump between solid and gas phases in a short temperature change. Mercury already proved it sheltered water, a volatile, but MESSENGER found others such as sulfur, potassium, and chlorine that easily vaporize at moderately high temperatures. These volatiles are distributed all across the surface of the planet. For its size, Mercury contains as much volatile content as other terrestrial planets in the solar system that are farther from the sun and hence much colder. Where the volatiles come from and how Mercury has retained them are still matters of scientific debate. Some researchers think that the volatiles came from underground relatively recently, while others think the chemicals have persisted on the surface since an embryonic Mercury condensed from its protoplanetary disk. The volatiles on Mercury raise questions. For example, if planets that edge up against their stars have volatiles, especially water, could these locales also be habitable? Well, it's possible that Mercury once held the ingredients for life. Indeed, Mercury has irregular depressions in the ground called hollows. Mariner 10 first glimpsed them in 1975. Then MESSENGER photographed these shallow tracts at fine resolution. The depressions span from a few dozen feet to over a mile across, and they may be as deep as 120 feet. They look like the soft, airy insides of a sourdough loaf cut open. The hollows may be the doing of volatiles, scientists theorize. Since the atmosphereless Mercury has no rain or wind to carve the land, surface features like hollows can only be formed from other processes, such as the ground leaking volatiles into space. Hollows are relatively young formations, about 100,000 years old on average, compared with some 4 billion-year-old impact craters on Mercury. Scientists think hollows are still forming today, and hollows are unique to Mercury. No other celestial body in the solar system seems to present similar pockmarks. In recent years, scientists have identified other structural formations on Mercury. Chaotic terrains, jumbled ridges that look like a failed game of Jenga, cut up vast swaths of the land. Some researchers think the chaotic terrains are the result of the ground wafting volatiles until it loses structural integrity and collapses. Other scientists think that chaotic terrains form after ripples from an asteroid impact encircle the planet and meet on the opposite side of the globe. In addition, Mercury's topography also provides clues that volcanoes once spewed lava on the planet. Mariner 10 first glimpsed and then Messenger later confirmed that glossy plains spread across Mercury's surface. Each plain suggests pooled lava smoothed over older craters and ridges. Researchers think that magmatic volcanism halted on Mercury anywhere between 1 billion to 3.5 billion years ago, due to planetary cooling and contraction that plugged up the magma's escape routes. Mercury has also shown signs of another kind of volcanism, explosions. If streaming lava is like a runny nose, then explosions are the volcanic equivalent of a sneeze. Irregular pits several miles across and more than 2 miles deep hint at ancient pyroclastic volcanoes that self-destructed. Scattered around these pits are deposits that researchers think are ejecta from the explosion. These types of volcanic bursts are probably caused by volatiles underground. When these buried chemicals rise to the surface, they expand in volume. Eventually, the pressure buildup of gases causes the volcano to pop, like an overfilled balloon. But volatiles, a chemical category that includes water, are essential for sparking and supporting life as we know it here on Earth. So, their potential presence on Mercury is an intriguing development. Astronomers now speculate that beneath the scorching surface of Mercury, the closest dwarf planet to the Sun, there could be signs of life. But how could volatiles, which are essential to life here on Earth, survive on a planet whose daytime temperatures soar to 430 degrees Celsius and drop to minus 180 degrees Celsius at night? Alexis P. Rodriguez, a researcher at the Planetary Science Institute in Arizona, explained that while the planet's surface swings wildly between temperature extremes, just below the surface, temperatures are milder. In the words of Rodriguez, it's likely that there was some sort of water that formed in part of Mercury's crust. But the team cannot yet tell exactly what volatiles were present when the planet's surface broke apart. While the mystery remains, a completely unexpected discovery made by NASA's Messenger spacecraft revealed that a 10-mile-thick diamond mantle may lie beneath the crust of Mercury. While instance of such valuable incrustation might sound tantalizing, turning these precious stones into fashionable jewelry remains an impossibility due to their inaccessible location deep within the planet. However, these gems could hold the key to unraveling some of the big unanswered questions circling around Mercury composition and its rather curious magnetic field. These diamonds may facilitate heat transfer between the core and mantle, thereby creating temperature differences and causing liquid iron to circulate, a process that would kickstart the creation of a magnetic field. The discovery of a potential diamond layer within Mercury opens new avenues for planetary research and composition studies not only of Mercury, but also of other celestial bodies. Understanding the unique geological characteristics of Mercury could provide deeper insight into the formation and evolution of the solar system. The next complication to the puzzle involving Mercury is that the large global scarps and wrinkles first spotted by Mariner 10 were also spotted by Messenger, along with much smaller version if the same structures. The scarps, first identified in 1974 and 1975, are hundreds of kilometers long and several kilometers tall, enormous cliffs towering over the landscape. The latest observations supplement those with scarps a few kilometers long and only tens of meters tall, and more importantly, geologically young. The larger scarps are ancient and softened by the passage of time, but the smaller ones are crisp and fresh, likely formed within the last tens of millions of years. This suggests that instead of being cold and dead, Mercury is still geologically active today as a hot core cools, the planet shrinks, and the surface crumples. But the story of Mercury gets stranger still. When mapping the geology of Mercury's surface, Messenger found distinct regions of unique geochemistry, a mix of terrains instead of a single, roughly similar surface. The spacecraft also spotted delicate volatiles like potassium and uranium, chemicals that should have been destroyed by the enormous heat of a crust-shearing collision or the scorching heat of a crust-boiling sun. By their very presence, these chemicals argued against either theory for Mercury's oddly large core, leaving scientists scrambling for a new theory. More data poured in from Messenger, with scientists identifying pyroclastic flows that could only be the result of explosive volcanism of lava mixed with volatile gases like water and carbon dioxide. More chemicals scientists didn't expect in abundance on a planet so near the sun. Soon after, the spacecraft's radar spotted water ice lurking in the shadows of polar craters, reminiscent to the ice hiding in polar craters of our moon. The Messenger mission came to an end in 2015, the spacecraft running out of fuel and deliberately crashing into the planet. Now scientists are left analyzing and reanalyzing the data from its 4005 orbits to try to piece together a new explanation for how Mercury formed that pull all these pieces together. But in all the mysteries lays a tantalizing new possibility for investigating this deceptively simple planet: quakes. If Mercury truly does have a hot, liquid core and is geologically active today, every time the crust moves to create a new ridge or wrinkle, a quake releases seismic waves propagating through the planet. On Earth, we detect that seismic energy with seismometers, observing the speed and distribution of the waves to map the planet's interior. Astronauts did the same thing on a smaller scale during the Apollo missions, observing moonquakes to understand what was going on below the surface. Scientists are planning to apply the same trick on Mars, sending a seismometer on NASA's delayed InSight lander to peer into the interior or Mars. This same idea could work on Mercury, with observations of seismic waves pinning down the true size and structure of the core, and detecting if, like the Earth, it has a warm liquid outer core around a solid interior. And if we can do that, we'll be one step closer to understanding how Mercury formed, why it is the way it is today, and what to expect of other rocky planets around distant stars. Another long-awaited mission is BepiColombo, a joint mission of the European Space Agency and the Japan Space Exploration Agency. It will be only the second and the most complex mission in history to orbit Mercury. Its two orbiters, the European Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter, carry a combined 16 scientific instruments that will help shed light on some perplexing questions. Do the scorched planet's polar craters really harbor water ice? Where does Mercury's magnetic field come from? What are the strange hollows on its surface? The mission, launched on October 19, 2018, is expected to reach Mercury in 2025, after a complicated 7-year journey, which requires 9 flyby maneuvers, including 1 at Earth, 2 at Venus, and 6 at Mercury itself. These flybys slow down the spacecraft against the gravitational pull of the Sun so that it can safely enter the orbit around the innermost planet of the solar system. During the epic journey, the two orbiters travel stacked on top of an ESA-built Mercury transfer module. The module, with its 15-meter solar arrays, supplies power during the interplanetary cruise. It is also fitted with 3 selfie cameras, originally used to monitor the deployment of the solar arrays and antennas after launch. But these cameras are regularly being used by the BepiColombo team to obtain simple black and white images of the spacecraft's whereabouts. Thanks to these cameras, Bepi Colombo is sending regular postcards home from its encounters with various planets during the flybys. In April 2020, the spacecraft waved goodbye to Earth during a flyby at a distance of 12,700 kilometers. In October 2020 and August 2021, Bepi Colombo flew past Venus. The first flyby saw the spacecraft zip by at a distance of 10,620 kilometers from Venus. However, the second took it incredibly close, only 550 kilometers above the hot, cloudy planet's surface. This enabled scientists to take some unique measurements of Venus's murky atmosphere. Once the stacked spacecraft reaches its destination, the MTM will separate from the orbiters. Then, the two spacecraft will each be put in separate orbits to perform scientific investigations of Mercury. Japan's MMO will have an orbit of 9.3 hours, and Europe's MPO an orbit of about 2.3 hours. The mission is expected to last for 1 Earth year, an equivalent of 4 Mercury years. It may be extended for an additional Earth year if funding allows, and the two spacecraft remain in good health. Elsewhere, scientists also expect our most powerful space observation to take some photos of Mercury. James Webb is made up of a 6.5-meter, gold-plated mirror, a sunshield that is the size of a tennis court, and an array of complex instruments that are cooled to temperatures only a few degrees above absolute zero. These features allow the telescope to observe the heavens in infrared radiation, revealing details of the universe just after its Big Bang birth 13.8 billion years ago, and images of stars being born in dust clouds. However, the telescope is providing science with a further gift. For infrared radiation also turns out to be ideal for studying extrasolar planets, or exoplanets, as worlds that orbit other stars are known. But how can Webb analyze exoplanets' atmospheres? We all know that measuring a planet's atmosphere from hundreds or thousands of light years away is not as daunting as it may sound, though it certainly requires specialized instruments and rigorous techniques. One method is known as transmission spectroscopy. Here's how it works. Webb will first observe the star itself to obtain its spectrum. Next, Webb will wait until the exoplanet passes in front of its star and then measure another spectrum. At this point, the exoplanet will be backlit, which means the light of the star filters through the planet's atmosphere toward Webb. The planet's atmosphere will absorb some of that starlight, which will appear as dips in the spectrum. When researchers subtract the spectrum of the star from the combined spectrum of the star and the exoplanet, they are able to isolate which light was absorbed when it passed through the exoplanet's atmosphere. Next, they will compare the light absorption dips with extensive references that detail the light absorption of every molecule we've witnessed on Earth to determine which molecules are present in the exoplanet's atmosphere. An early target for astronomers using the James Webb has been TRAPPIST-1, a small, cool star of a type known as a red dwarf. 40 light-years from Earth, it has a family of 7 small rocky worlds, 3 of them lying within a region known as the habitable zone. Here, conditions are not too hot and not too cold to prevent water from existing as a liquid, a prime requirement for life to flourish, say astrobiologists. However, analyses using the James Webb of 2 of the star's innermost planets, TRAPPIST-1b and TRAPPIST-1c, have revealed they possess either no atmosphere or only a very thin one. Further Webb studies of the rest of the system are now being planned. TRAPPIST-1's system still looks promising if you are seeking a world that might support life, said astronomer Dr. Joe Barstow of the Open University. However, one special problem does affect studies of stars like TRAPPIST-1. Red dwarfs are spotty. This may not sound like a terminal condition, but it does have serious implications. As Barstow said, our own sun has sunspots that are associated with intense solar activity, but it has relatively few. By contrast, TRAPPIST-1 has dozens of spots that change all the time, and that makes it very difficult to differentiate between these and features of a planet's atmosphere. the TRAPPIST-1 system is not going to give up its secrets easily. Ultimately, astronomers using the Webb telescope to seek out signs of extraterrestrial life are looking for a set of biological markers known as the Big Four: oxygen, carbon dioxide, water, and methane. Their presence in the atmosphere of an exoplanet would be a strong sign that life of some kind exists there. The life of the James Webb Space Telescope promises to be an intriguing one and lengthy. James Webb's flight on an Ariane 5 rocket from the European Space Agency's launch pad in Kourou in French Guiana to its current position in orbit round the Sun was near flawless. The observatory used very little fuel to maneuver itself into its exact target location, and that means there will be extra to allow the telescope to orient itself for far longer than anticipated. Space engineers have calculated Webb's expected 10-year lifetime could be doubled. In many ways, that is very good news. We will be able to do a lot more science with it now. We are going to learn so much about the chemistry of their atmospheres and are going to find some very strange and bizarre worlds out there. It is tremendously exciting. And if one day astronomers announce they've found an Earth analog among the stars, what's next? The implicit part of the question is whether we can travel to it and live there. But simply put, we can't. It's not like we can go there. There's no USS Enterprise we can use to warp over to the nearest Earth 2.0, and without faster-than-light travel, it would be a long trip. Even the fastest spaceship ever launched would take the better part of a millennium to get to the nearest star system, Proxima Centauri, which does actually host an Earth-sized planet that might be within our range of acceptability. Better pack a lunch. So many sci-fi movies tell us we need to evacuate Earth that it's a trope. This idea is far more fi than sci, though. Humanity increases its number by more than 70 million people every year. You'd need to launch 2,000 SpaceX starships every day just to keep up with that increase, even ignoring the less than helpful travel times. Easing population pressure via interstellar immigration is a non-starter. Establishing a settlement is a tall order, too. We don't even really know how to do this in low Earth orbit, on the Moon or on Mars. We're a long, long way from being able to set up shop on an alien Earth, even if we could easily get to one. Regardless, what's important is that it may also help us answer the most fundamental question humans have ever had. How did we get here? For millennia, this question has inspired speculation, myth, religion, and philosophy. With a distant blue-white world hovering in the eyepiece, it becomes science. So, scientifically speaking, we look for other planets because we want to understand how they form, how conditions change their physical properties, and how they differ from or mirror the planets in our own solar system. On July 20th, 1969, Neil Armstrong and Buzz Aldrin safely descended onto the Moon in Apollo 11. It was a frightening moment, with alarms firing and gas lines freezing as the astronauts barreled toward another celestial body for the first time in human history. The astronauts landed on Mare Tranquillitatis, a dark, bluish plain made of ancient lava, and for the next 2 hours, they explored the Moon's surface, collecting rock samples and bouncing about. It was the first of 6 more manned journeys to the Moon between 1969 and 1972. Apollo 13 was the only mission that had to be aborted, with the crew making an emergency re-entry. In 1972, Apollo 17 was the last manned expedition at a time when U.S. interest in lunar landings was fading fast. We'd been there, and now it was time for the next big space adventure. But now, half a century later, scientists have a renewed interest in what we can learn from the Moon. According to NASA, the Moon continues to be a treasure trove of science, one that might in the future allow for habitation. What's more, the Moon turned one side of itself away from the Earth 4.4 billion years ago and never looked back. This cosmic insult has turned the Moon's far side into a mysterious, troublesome place where, at least in the imaginations of sci-fi writers and human-hating robot aliens, crashed. That it is so close, yet so unexplored, lends the far side of the moon a shadowy mystique. But now, thanks to the James Webb Space Telescope, we can finally see what lies beyond the horizon, unlocking a new era of lunar exploration and discovery. Join us as we explore the mysterious realm of the moon's dark side, uncovering obscure details and highlighting our celestial neighbor's lesser-known features. From Earth, we only ever see one lunar face, because the moon takes about the same amount of time to rotate once as it does to complete a single orbit of Earth. This is no coincidence. It's linked to our planet's strong tidal influence on our natural satellite. The result is that, more or less, we can divide the moon into two hemispheres, the side that always faces us, the near side, and the one that always points away, the far side. Anyone who has gazed up at the moon is familiar with the near side's most prominent features, many large and roofly circular dark patches against a backdrop of brighter terrain. Ancient astronomers dubbed these dark features Maria, Latin for seas, because of their water-like appearance from Earth. But they're actually plains of basaltic volcanic minerals, solidified lava, that erupted out from beneath the surface long ago. The near side's brighter regions are older, heavily cratered, and more reflective highlands that rise from the plains. Astronomers had long assumed the moon's mostly unseen face was similar, but space-age reconnaissance shattered those expectations in 1959, when the Soviet Luna 3 spacecraft beamed back the very first image of the far side. Although it was grainy and fuzzy, the photograph was still clear enough to reveal a wildly different landscape. The far side was almost all rugged highland, with the near side's sprawling Maria shrunken to just a few scattered darker spots. Decades of follow-up observations only widened the shocking mismatch between the hemispheres. For instance, gravity data from the two lunar-orbiting GRAIL, Gravity Recovery and Interior Laboratory, spacecraft indicated that the far side's crust was about 20 kilometers thicker on average than that of the near side. Why were the two hemispheres so different? It's tempting to think Earth's tides played a role, yet nothing is ever that simple. The cause must reach back to the moon's birth. The current origin story, widely accepted by scientists, is called the giant impact hypothesis, also known as the Big Splat, which I rather like. In this scenario, a Mars-sized world, which astronomers call Theia, after the Titan who was the daughter of Gaia in Greek mythology, slammed into Earth at a grazing angle shortly after our planet's formation 4.6 billion years ago. The immense release of energy tore Theia apart, sinking its core down into Earth's depths and blasting its outer layers, plus lots of terrestrial material, into orbit. All that superheated rock cooled rapidly in space and became the moon. Scientists still argue over the details, but our satellite may have coalesced from the debris in as little as a few months to a few years. At that time, the moon was much closer to Earth than today, perhaps only about 1/10 the current separation. Across the eons, tidal forces gradually pushed it farther out. At that close distance, the tidal interaction between the two was fierce, and the newly created moon's rotation may have become tidally locked in as little as a year. This is far faster than the crust could have formed and solidified, which means that the hemisphere dichotomy couldn't be caused by Earth's tidal pull. Something else must have happened to thicken the far side as the crust initially cooled. However, scientists tossed around a few ideas. None proved to be a perfect fits for the dichotomy we see today. Perhaps a second, smaller moon formed from the big Splat's debris as well, and it eventually collided with the bigger moon at slow speed and drapped the far side with more material. Maybe physical processes churning inside the newborn moon allowed one side to get thicker. Then, in 2014, a team of astronomers published a new, arguably better explanation. Their culprit was not our planet's tides, but Earth itself. In all the models investigating the young moon's evolution, none had completely taken into account that Earth loomed overwhelmingly large in the lunar sky. Shortly after the moon formed, Earth was so close that it would have taken up a staggering 40 degrees of angular diameter in the sky as seen from the moon, covering a celestial area 20 times larger than it does today. Remember, at that time, Earth was hot. Theia's impact would have vaporized much of our planet's surface and melted the rest. For many centuries, if not millennia, the heat from rock, boiling at about 2,000 degrees Celsius, would have cooked the nascent moon's near side, raising it to about 1,000 degrees C, while the far side would have cooled to frigid temperatures. This has profound implications. Early on, when the moon was still entirely molten, it would have had a churning atmosphere of incandescent rock and metal. Hardy elements such as calcium and aluminum have a very high boiling point and would have stayed as gas on the moon's roasting near side, whereas they would have easily condensed on the cooler far side. Those windswept elements would have interacted with others on the far side, forming relatively lightweight minerals such as feldspar, which would have floated on the surface to gradually create that side's thicker crust. Interestingly, orbital surveys do show more feldspar on the far side than on the near side. Also, this process could have concentrated other minerals on the near side, including radioactive ones that would have acted to heat the crust there and allowed magma to eventually burst forth. This would have flooded much of the near side's surface to make the dark Maria while leaving the far side mostly Maria-free. So, does this solve the mysterious lunar dichotomy? It's the best idea going right now, but of course more evidence is needed to support it. And James Webb may provide some clues. The technological achievement of NASA's time machine is uncontroversial. It's set to take the success of the Hubble a step further. What we get now is a telescope that's about 100 times more powerful than Hubble. The Webb's biggest advantage is the type of light it collects. Light comes in a lot of different varieties. The human eye can see only a narrow band known as visible light. But the universe contains lots and lots of light outside this range, including the higher frequency, higher energy forms, ultraviolet gamma rays. Then there's the lower energy light with longer wavelengths, infrared, microwaves, radio. The Hubble Space Telescope collects visible light, ultraviolet, and a little bit of infrared. The Webb is primarily an infrared telescope, so it sees light that's in a longer wavelength than what our eyes can see. This seems nerdy and technical, but it's actually what allows Webb to look further back in time than the Hubble. Infrared light is often very old light due to a phenomenon called red shifting. When a light source is moving away from a viewer, it gets stretched out, morphing into a longer and longer wavelength, growing redder. The opposite is true as well. As a light source grows closer, the wavelengths shorten, growing bluer. It's similar to what happens when a siren goes by. The pitch increases as the siren approaches, then decreases as it trails away. Because space is constantly expanding, the farthest things away from us in the universe are moving away from us. Imagine a star that's really far away. The light from that star may start off in the visible spectrum, but it gets stretched on its journey to us. It grows redder and redder. Eventually, these very distant old galaxies grow so red that they drop into the infrared spectrum. Webb can see this ancient light that has become invisible to the human eye. Conveniently, infrared light has other uses as well. It's a really good type of light to use to look at exoplanets. For instance, if you were on a planet that orbits another star and wanted to see Earth, visible light wouldn't be your best bet. That's because the Earth peaks in the infrared. So, if we want to be able to study an Earth-like planet in another solar system, what we really want to do is observe at infrared wavelengths, because that's where the light from the Earth is being emitted. And in a recent discovery, scientists have for the first time discovered a cave on the moon. What's interesting, it is just one in probably hundreds of caves hidden in an underground, undiscovered world. And that's a piece of good news. Anyway, countries are racing to establish a permanent human presence on the moon, but they will need to protect astronauts from radiation, extreme temperatures, and space weather. And at least 100 meters deep, the newly discovered cave could be an ideal place for humans to build a permanent base, and suggested humans could potentially be living in lunar pits in 20-30 years. That's convincible. After all, life on Earth began in caves, so it makes sense that humans could live inside them on the moon. Fascinatingly, it is visible to the naked eye from Earth, and is also where Apollo 11 landed in 1969. The cave has a skylight on the moon's surface, leading down to vertical and overhanging walls and a sloping floor that might extend further underground. It was made millions or billions of years ago, when lava flowed on the moon, creating a tunnel through the rock. The closest equivalent on Earth would be the volcanic caves in Lanzarote, Spain. The cave has yet to be fully explored, but the researchers hope that ground-penetrating radar, cameras, or even robots could be used to map it. The future research of that cave may also help us explore caves on Mars in the future. That could open the door to finding evidence of life on Mars, because if it did exist, it would almost certainly have been inside caves protected from the elements on the planet's surface. The moon cave might be useful to humans, but the scientists also stress that it could help answer fundamental questions about the history of the moon and even our solar system. The rocks inside the cave will not be as damaged or eroded by space weather, so they can provide an extensive geological record going back billions of years. But besides the moon, James Webb also focuses its sharp eyes on moons outside the solar system. These are known as extrasolar moons, or simply exomoons. Thus far, exomoons have proved an elusive subject for astronomers because they are hunted using the same light-blocking technique employed to spot exoplanets around stars. However, this technique is difficult enough when looking for large worlds beyond Earth. Searching for little exomoons with it is immensely challenging. Not only would exomoons block far less light than the exoplanets they orbit would, but they'd also need to be in the right position at the right time. An exomoon that's detectable would have to be orbiting its planet precisely as that planet's crosses, or transits, the face of its parent star to obscure some light when viewed from our vantage point in the cosmos. That obstruction would be detected by scientists' equipment, which would allow them to reverse calculate that an exoplanet, or potentially exomoon, gave rise to it. But now, with James Webb's near-infrared imager and slitless spectrograph, or NIRIS for short, scientists can make the first undisputed detection of an exomoon. This is hopefully just the beginning of the exomoon revolution. New worlds that will surely hold some remarkable secrets. Of course, Webb's Cycle 3 GO projects also include a wealth of investigations focusing on exoplanets themselves and not just their potential moons. This includes a few that wish to determine whether some exoplanets have the conditions needed to support life as we know it. Among those exoplanet habitability projects is one called Constraining the Atmosphere of the Terrestrial Exoplanet TOEI 4481b. This will use Webb's MIRI instrument for 16 hours to determine if a roughly Jupiter-mass exoplanet, which orbits a star around half as massive as the Sun that sits some 39 light-years away, has been able to hang on to its atmosphere. The result could serve as a first step in understanding the habitability of rocky planets and establishing whether M-type stars, also known as red dwarfs, have terrestrial planets with significant atmospheres. This is important in the search for life beyond Earth because red dwarfs are the most common stars in the Milky Way. In addition, supermassive black holes are getting in sight of James Webb. Astronomers widely believe the majority of our universe's large galaxies have supermassive black holes in their hearts, with masses as great as millions or even billions of suns. Some of these supermassive black holes are actively swallowing gas and dust that surrounds them in disks of matter called accretion disks. These monster black holes' gravitational influences are thought to heat the material in those accretion disks, causing them to emit bright radiation across the electromagnetic spectrum and create regions called active galactic nuclei, or AGN for short. Additionally, any matter that isn't swallowed by the black hole can be channeled to its poles, where it is blasted out as jets of particles traveling at speeds approaching light. When that happens, the phenomenon is called a quasar. The violent conditions of these events make AGNs and quasars the brightest objects in the universe, often luminous enough to outshine the combined light of every star in the galaxies around them. Our theoretical understanding of supermassive black holes has burgeoned since the Event Horizon Telescope revealed the first image of a black hole, the supermassive black hole at the heart of the galaxy, Messier 87, in 2019. And James Webb's Cycle 3 missions will further contribute to this knowledge. The Webb Cycle 3 supermassive black hole observation programs include the investigation of quasars in the early universe and the nature of the first black holes. Scientists hope to understand how those black holes may have influenced the growth of galaxies over billions of years. The observations of supermassive black holes in the early universe, made by the Webb telescope, could also reveal how these cosmic titans grew to the tremendous masses scientists observe before the universe was even 1 billion years old. Such a question can be answered by using MIRI to investigate if a giant molecular cloud that existed around 13.2 billion years ago could have directly collapsed, birthing a heavy black hole seed that would account for a rapid growth mechanism. One of the primary roles of James Webb is investigating objects in the early universe. The powerful space telescope has this capacity because the expansion of the universe stretches wavelengths of light from distant objects as this light travels toward us, moving the wavelengths toward the red end of the electromagnetic spectrum. The longer that light has traveled to reach us, the more red-shifted the light has become. This means light that has been traveling for around 12 billion years is extremely red-shifted all the way into the infrared region of the electromagnetic spectrum and outside the visible range we can see with the unaided eye. Effectively, infrared light is invisible to us. However, the observatory is capable of observing this infrared light, and thus helps to investigate the first stars and earliest galaxies, something it will continue to do in 2025 with several Cycle 3 GO projects. Though James Webb was designed with the study of distant objects in mind, its next mission will also see the observatory used to study bodies within our own solar system. These will include hunting for the source of gas plumes coming from Saturn's moon, Enceladus, investigating the dynamics of the Uranus's rings, and characterizing icy objects that exist in the Kuiper Belt at the very edge of the solar system. These studies attract even more attention when scientists have long theorized that both Enceladus, one of Saturn's 146 known moons, and Europa, one of Jupiter's 4 large Galilean moons among its total 95 moons, could host vast liquid water oceans that harbor life. If this is the case, then complex organic molecules like amino acids and nucleic acids, the building blocks of life as we know it, could serve as biosignatures of life on the worlds. The problem, however, is that both Europa and Enceladus are bombarded by harsh radiation from the sun that could potentially destroy complex organic molecules at their surfaces. But new research offers some hope on this front, suggesting that those biosignatures could indeed survive if they're preserved in the icy shells of the moons. And if that's true, these molecules could sit so close to the surface that future robotic landers may be able to dig them free. At Enceladus, in fact, this digging might not even be needed. Biosignature molecules could survive in shallower ice than on Europa. As research leader Alexander Pavlov of NASA's Goddard Space Flight Center in Greenbelt, Maryland, said in a statement, "Based on our experiments, the safe sampling depth for amino acids on Europa is almost 8 inches, or 20 centimeters, at high latitudes of the trailing hemisphere, the hemisphere opposite to the direction of Europa's motion around Jupiter, in the area where the surface hasn't been disturbed much by meteorite impacts. Subsurface sampling is not required for the detection of amino acids on Enceladus. These molecules will survive radiolysis, breakdown by radiation. At any location on the Enceladus surface less than 1/10 of an inch, or under a few millimeters from the surface. In short, James Webb is opening a new era in astronomy. Astronomy as a field aims to answer big yet fundamental questions about our place in the universe, so it is perhaps most apt to start this list with a bombshell discovery 25 years ago, on April 15, 1999, when astronomers found the first planetary system outside our own. In the past 25 years, astronomers also discovered hundreds of free-floating worlds that challenge the definition of a planet, the long-sought God particle, ripples, in the fabric of space-time, the sun's missing neutrinos, the first real clue about the nature of dark energy, and a lot more. Here's a look back at the most amazing astronomical discoveries of the past quarter century. 1. First planetary system outside our own. In April 1999, astronomers found a trio of Jupiter-sized planets circling the sun-like yellow-white star Upsilon Andromeda A, located roughly 44 light-years from Earth, the first extraplanetary system ever to be discovered. The discovery disproved the notion that our solar system was a singular phenomenon in the universe, and offered compelling evidence that the discovery of other planetary systems was only a matter of time and technology. In 2010, astronomers also found that unlike the planets in our solar system, the Jupiter-sized planets in this extrasolar system do not orbit in the same plane. Rather, two are inclined by 30 degrees with respect to each other, the first such orientation ever spotted, which helps astronomers refine theories of planetary formation and evolution. As of April 2024, astronomers have found close to 900 stars that host 2 or more planets. 2. First free-floating planet in the Milky Way. At the turn of the 21st century, astronomers detected the first free-floating planet hovering by itself in the nearby Trapezium cluster, a stellar nursery near the heart of the Orion Nebula. In our galaxy alone, there may be as many as a quadrillion of these rogue planets, which are kicked out of the star-circling disks of gas and dust in which they are born. However, only a handful have been found cruising through our galaxy. Because they are ultra-faint, they are difficult to spot. The orphaned planets are the lightest products of a star's birth and important carriers of information about the environments where they formed. First exoasteroid belt outside solar system. In early 2001, NASA's Spitzer Space Telescope found evidence of the first asteroid belt outside the solar system around the nearby sun-like star HD 6983, located roughly 40 light-years away in the constellation Puppis. The belt is estimated to be 25 times more massive than the main asteroid belt between the orbits of Mars and Jupiter. In 2005, astronomers discovered 3 Neptune-like planets orbiting this star, with the outermost planet possibly within the star's habitable zone. Astronomers are interested in the size and location of asteroid belts in multiplanetary systems, as the rocky shards influence the coalescence of planets and even the emergence of life. In our own pocket of the cosmos, a leading theory posits that asteroids delivered water and organic compounds to early Earth, which is supported by recent detections of water molecules in asteroid samples returned to Earth as well as a couple in space. 4. Mystery of sun's missing neutrinos solved after 30 years. In June 2001, physicists announced that they had found the sun's missing neutrinos, subatomic particles that have no charge and practically no mass. The detection ended a 3-decade-long search for the tiny packets of energy, but implied they must have a bit of mass. Nuclear reactions at the sun's heart, the same process by which the sun shines, produce billions of neutrinos, half of which were estimated to make the 93 million mile or 150 million kilometers journey to Earth. But experiments during the late 1960s detected too few of the ghostly particles, a discrepancy that came to be known as the solar neutrino problem. In 2001, experiments from the Sudbury Neutrino Observatory in Canada revealed that the missing neutrinos had, in fact, merely transformed into two other types of neutrinos on their way to Earth and escaped detection. This transformation demands that the ubiquitous neutrinos possess some mass, now estimated to be hundreds of thousands of times less than the mass of the next lightest particle, the electron. 5. First exoplanet blanketed by an atmosphere. In November 2001, astronomers entered a new phase of exoplanetary science when data from the Hubble Space Telescope revealed for the first time the presence of an atmosphere blanketing an alien world. The exoplanet, HD 29458b, is located 150 light-years away in the constellation Pegasus. It was the first of many exoplanets now known to host atmospheres ranging from vanishingly thin to very dense, like Jupiter's. The discovery sparked a new era in exoplanet exploration, as astronomers could begin to compare exoplanets' atmospheres, including the abundances of atmospheric gases known to emerge from life on Earth. 6. Fast radio bursts reveal the universe's missing mass. In 2007, astronomers using the Parkes Observatory in Australia discovered a fast radio burst known as FRB, a bright, incredibly short burst of radio waves from a galaxy billions of light-years from Earth. In just milliseconds, the intensely bright pulse, named Lorimer Burst FRB 10724, blasted into space as much energy as the Sun does in 80 years. Since then, hundreds of such intensely bright pulses have been detected from faraway galaxies scattered across the universe, including a few that seem to erupt repeatedly and irregularly. Astronomers have used the intense pulses to find some of the universe's missing matter, which lurks in spaces between galaxies and was detected by studying the dispersion of radio waves from FRBs as they traveled through interstellar gas. 7. Discovery of the Higgs boson, the God particle. In July 2012, the field of particle physics captured the global spotlight with the discovery of the Higgs boson, a long-sought subatomic particle that pervades the universe as a field that gives other elementary particles their masses. The existence of the Higgs boson was first predicted independently by physicists Peter Ware Higgs and François Englert in 1964, close to half a century before it was found by two experiments at the Large Hadron Collider in Switzerland, which detected the God particle within just 2 years of beginning operations. Higgs and Englert received the 2013 Nobel Prize in Physics for their theory of how particles acquire mass. 8. Detection of gravitational waves confirms Einstein's theory. In February 2016, scientists using the Laser Interferometer Gravitational Wave Observatory announced that, in September 2015, they had detected gravitational waves, faint ripples in spacetime predicted by Einstein a century ago. For the first time, when those that emerged from colliding black holes washed over Earth. Because these waves traveled unscathed through sizzling matter of the early universe, their detection heralded a new way of studying the universe that was never possible with electromagnetic waves. 3 astrophysicists who helped detect the gravitational waves, Rainer Weiss, Barry Barish, and Kip Thorne, won the Nobel Prize in Physics in 2017 for their work. Another new era in gravitational wave astronomy began in June 2023, when scientists with the North American Nanohertz Observatory for Gravitational Waves Collaboration revealed compelling evidence for the presence of a faint but persistent hum of gravitational waves pervading the universe. They strongly suspect the hum, which, at 1/1,000,000th of 1 Hertz, was a few hundred times fainter than the gravitational waves detected in 2015, represents a collective echo of supermassive black hole pairs circling each other in orbits that shrink across millions of years. 9. First interstellar visitor spotted in our solar system. In fall 2017, astronomers spotted a strange object zipping through our solar system, the first known interstellar visitor. The identity of the object, dubbed Oumuamua, was shrouded in mystery because its brightness varied more than what would be expected from an asteroid, and it didn't act like a comet. As such, it sparked arguments, with some speculating that it might be an alien artifact. First considered an asteroid, Oumuamua was recast as a comet in 2023, with one group of astronomers suggesting it was likely ejected from an extrasolar planetary system and accelerated by tiny amounts of hydrogen gas emerging from the object's icy heart. In 2019, astronomers found the second interstellar visitor, Borisov, which was soon confirmed to be a comet, thanks to its telltale gaseous coma. The rogue object, which never passed near a star until visiting the Sun, is considered the most pristine comet ever studied. 10. First image of a supermassive black hole. In 2019, astronomers photographed a black hole for the first time. The Event Horizon Telescope project imaged the contours of the monster black hole lurking at the heart of the Messier 87 galaxy, which is located over 50 million light-years from Earth. The image opened up a new way to study black holes and was likened to the first illustrations of what insects and plants look like through a microscope. In 2021, astronomers unveiled a new image of the object that shed light on how magnetic fields behave close to black holes. In 2023, the black hole image got an AI makeover, which turned the fuzzy orange donut into a skinny ring. Astronomers also found that the black hole is spinning, although the rate of spin remains unclear. 11. The most detailed map ever of Milky Way. The most detailed map ever of the Milky Way plotted in 3D, nearly 1.8 billion stars in unprecedented detail using data from the European Space Agency's Gaia spacecraft. As mind-boggling as the 1.8 billion stars may be, they represent just over 1% of our entire galaxy's stars. Astronomers say studying the motions of these plotted stars could reveal long-sought clues about the nature of dark matter. 12. First starless, empty galaxies. In January 2024, astronomers announced that they had spotted a primordial galaxy that is so diffuse that it hasn't formed stars. The discovery challenges leading theories of how galaxies form and evolve and even the conventional definition of a galaxy. After all, what is a galaxy without stars? The same week, a different team reported the discovery of another almost empty galaxy called Noob, which is Spanish for cloud. Unlike our galaxy's central bulge, Noob is puzzlingly uniform and intriguingly isolated roughly 300 million light-years from Earth. Its closest large neighbor is at least 1.4 million light-years away. Such dark galaxies, which were once thought to outnumber all visible galaxies, shine hundreds of times fainter than the Milky Way, whose light is powered by roughly 100 billion stars. Astronomers continue to puzzle over why these ghost galaxies lack stars, even though they contain pristine star-forming gas. 13. Dark energy may be evolving. Physicists have long considered dark energy, the mysterious force driving the accelerated expansion of the universe, a cosmological constant, meaning it remains constant throughout the history of the universe. However, in April 2024, astronomers who created the largest 3D map of the universe suggested that dark energy may be evolving with time. The discovery might be the first real clue about the elusive phenomenon in the past 2 decades, and one that would be as revolutionary as the discovery of the accelerated expansion of the universe itself, if confirmed with future data, scientists said at the time. 14. James Webb's revolutionary discoveries. Astronomers have long wondered just how the universe resurfaced from the cosmic dark ages, when the cosmos was cloaked in dense fog of neutral hydrogen gas, to make way for the first starlight. In early 2024, astronomers using the James Webb Space Telescope revealed dwarf galaxies that existed in the first few 100 million years, packed enough punch to flood the early universe with its first light. The discovery is a remarkable testament to the telescope's unprecedented infrared capabilities that allow it to collect light from the faintest objects. Webb's amazing discoveries and breathtaking views have stunned the world since the observatory began operations in 2022. For instance, the telescope captured the pillars of creation, revealing in stunning detail both the colorful tapestry of the dusty cloud formation and the cosmic processes occurring in the region. As astronomer Derek Ward Thompson put it, the image can be likened to taking the X-ray of a human. James Webb continues to awe astronomers and the public alike with its detailed images of the most distant galaxies in the universe, faraway supermassive black holes, exoplanets, and more. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.